Yay. Okay, well, we're here to talk about Cassandra, which is an open source NoSQL Apache Kafka. I'm sorry, Kafka, yikes. Apache um, Foundation software. It is a database solution, and it's usually viewed, I think, in direct opposition to relational databases. So let's just dive right in. And the first thing is kind of this is our agenda. So I'm going to introduce myself just a little bit. And then we're going to talk about what a relational database is and kind of what we think about when we think about kind of the norms of relational databases. So then we can then talk about NoSQL databases and Cassandra specifically. We'll talk about the structure, we'll talk about the strengths, and I'll kind of wrap it up. And if you have questions, I just want to put this out there. If you have questions, feel free to it's not even interrupting. This is really a conversation. But if I go over something and it doesn't really make sense, or you'd like an example, please feel free to come off mute and say something. So just an introduction to me. I am a software engineer. I work at a consulting company called Accenture Federal Services. All we do is federal work. I'm a backend Java developer, and I am lucky enough that I get to work with Cassandra every day. And I just wrote a bunch of things for my tech stack up there. I to kind of a non-traditional, I guess more traditional now, like or more and more conventional now, path to becoming a developer. I went through a bootcamp called Launch Code. I was then a TA there. I have been a Scrum Master in the past, a bookstore manager for many years at an independent bookstore in St. Louis called Left Bank Books, and I was a project manager in the past. So I have a very back-end view of Cassandra, so that might color a little bit what we talk about today, but just heads up about that. Okay, so the first thing we'll talk about are relational databases. So can I ask here in this group, and feel free to not answer if you don't want to, but how familiar would everyone say that they are with relational databases? Do you use SQL? Do you work with databases in your work? As a human being who is like alive in the year 2024, we probably don't realize how much we come into contact with relational databases many, many times a day. But does anybody here work with them? No, maybe. Well, no worries. I will go over them at a high level. So relational databases are kind of what we think of as like normal databases. Like this is, when you think of, when you have an idea in your head of what a table is, for example, you probably see, a row that has column names, a column that has all your columns and your rows. And so that is what you have in your mind, in your mind's eye, is probably a relational database. And so the thing about relational databases that is probably most important is that, or most relevant to this discussion, is that they have what's called referential integrity, which means that in the schema of your database, which is like the roadmap of your database, um, the tables all have like a strict relationship to one another. So in a relational database, your data, whatever your specific piece of data is located in only one place. This is what's called normalization, which is normalization is like a set of conditions that your relational database must meet in order to be considered like good, or not. They call it normal form. So there are different degrees of normal form. Most people, when you're thinking about a database, you're thinking about a third normal form database. And that means a number of things. Like there are a bunch of different conditions. Like you can only have one piece of information in each cell, one value in each cell, or you will have a primary key for your table, um, or or that your tables or that the values in your tables can only be found in one place in your schema. So when I say a specific piece of information can only be found in one place, what I mean is like think of a table that has, or think about a piece of information like your name, right? So if we have a table, let's say we're running a bookstore, and again, I worked at a bookstore, which is why I think probably a lot of these examples are going to be bookstore related. We speak of what we know. But let's say you're running a bookstore, you have customers, and in a relational database model, you probably have in your software in your database, you probably have a table for your customer names. You probably have a table for your inventory. You probably have a couple tables for your inventory. So let's say you have an author table that has their names and like maybe an ID number assigned to them. You might have another table that has your books and another ID number assigned to them. You might have another table that has your customers in it and an ID number, unique ID number assigned to them. That's sort of what's considered normal form, where everything is like parsed out to where these tables are super specific. And if you go looking for Wintaye Gebru, if Wintaye Gebru is a customer of yours, if you go looking for Wintaye Gebru's phone number or her address, you've got to go to the customer table. Like it's only located in the customer table. If you want to recall records and have that as part of your view, part of the information that you pull back, that you've got to reference that table specifically. So if what you're wanting to pull back is like order information, and you'd like to have as part of the records that you pull back, you'd like to see like, well, I'd like the order number, I'd like the customer's name, I'd like their shipping address. And that information is scattered about in a couple of different tables because again, you have a customer table and you have an order table or a book table. You would normally join that information via the aptly named command join. And then there are other SQL commands like group by and order by that you might use to kind of tweak your data so that it comes back to you in a useful form. So that's all totally fine. That happens constantly, but that data, you're literally going to wherever specific address that like data is located in and pulling it back from there and saying like, I'd like it all in one place. So that is like a typical relational database. And so when we say referential integrity, we mean that all of these things are in their right place in their separate tables. And if you need that information, you refer to it by its like table name and column name. And so normal database. And then the other thing here, so you query based on these tables, you're constrained by their structure. So you can't query something from a table that it doesn't exist there. You can't query like a number from a table whose column only has strings, or you know what I mean, like an integer. If you're looking at a column that only has strings, it's relational databases are notoriously only vertically scalable, which means that if you want a larger database, if you want to run more queries on this database, you probably have to change the physical components to your server. Like you might want to increase the CPU power, you might want to increase the memory. these are like actual like physical upgrades probably, or add a server or something like that. They're physical upgrades that you'd have to make, which are very costly. So that is another thing that relational databases are kind of known for. And then the sort of the other thing about them is that they're schema, which we kind of talked about before, but I don't think it's very, if you haven't worked with a relational database, you might not know the term schema. A schema is, I think I said before, like the roadmap to your database. It's literally like it's the listing of all of your tables, all of your field names, all of their data types, your indexes, everything that's found, not the values, but like everything that's found that makes up the structure of your database would be considered your schema. And so once your schema is set, they are inflexible, they don't change. So that's kind of relational databases in a nutshell. Does anybody, oh, and the other thing is I mentioned here that you update sortation in a query. Relational databases are basically when they store your records, like you insert into table A, one record, they're not, they are unordered. So they're just adding them in almost like append only style. They just add them in, and it's not until you call these records back that they are ordered. So if you've ever used like SQL Developer or something like that, Oracle SQL Developer, or something to query a relational database, you might have noticed that you can use terms like order by or group by or something like that. You can use that to kind of manipulate the records that you get back and how you view them. That's all done in the query. It's not done in the table. In the table, like how they're actually saved and stored is unordered. Can I stop there? Does anybody have a question about that, about relational databases?
I'm going to jump in. We do have a couple questions in
Oh,
chat,
yay.
which
Huzzah.
so let's jump in there. So one of them was, how does sharding and partitioning apply to relational databases, or does it not? Does it only apply to non-relational? That came from Lawrence.
That's a great question. So partitioning, I don't think I'm familiar with the term sharding, but I think it probably means a similar thing to partitioning. So we're going to use the word partition in two different ways. So I'm not sure how you're using it here. Lawrence, do you mean partitioning in the sense that like we are partitioning up data so that we can make it workable and make it a workable size? Or do you mean partition in the sense, in like the database sense of like network for scalability? Yeah, so there there are, okay, so then you probably mean like how we break up data and how we store it. And if that's the case, we are going to get into it in just a second. I have a whole, you'll like this. I have a whole a slide on partitioning. Um, but how does it relate to relational databases? Relational databases don't partition data in the same way as NoSQL. So it's not really it's not really, when you think about relational databases, you don't think about partitioning, because the whole thing about NoSQL, which we'll get into in just a second, is that you can break up your data and access it individually via these partitions. And that's what we mean by a distributed database. So relational databases are not distributed. And so partitioning, um, when met in this way, does not is not apt for relational databases. Does that make sense?
He gave you a thumbs up. I don't know if you could see that.
Yay. Yeah. Okay, excellent.
Yeah.
Great. Okay. Any other questions? Oh, Jeff. Okay, so Jeff is very familiar. So, Jeff, if I am not, I'll tell you right now, I have a real layman's familiarity with relational databases. I use them for just a little bit. I mean, I use them the way that that people normally use them. But I have never created my own like enterprise level relational databases, and I certainly haven't used them for decades. So please feel free to, oh, yep, okay. Let's move on. Okay, so how is Cassandra different? So just kind of a NoSQL high-level overview. NoSQL, which is sometimes called, people refer to it as like not SQL or not just SQL. There are a lot of different ways to refer to it, but basically what they mean at a high level, or what people mean by NoSQL, is that it's schema-less. So what I was just describing about the schema for relational databases, where you have like sort of a set and inflexible list of everything that's located in your database, doesn't really apply to Cassandra. It is, you can have, and a really good example of that is in a given table, you can have one record that has a string for a data type on one row, and then on the next row, you could have, in that same column, you could have a collection or something like that. It is where in relational database, you would never have that because the type of that column is already set. The type of the data type that you might get back is already set. It is denormalized. And so this is kind of a big thing. So normalized relational databases, it is a big no-no to have the same information in a bunch of different places. In NoSQL, it's essential. Like the whole thing about NoSQL is that we are not going to take the time. We have no referential integrity. So these tables don't know what the other tables are doing, and they don't care. In a relational database inside your schema, the tables all know what each other are doing because they refer to one another. And NoSQL and what's called a key space, which is kind of similar to a schema. These tables are all standalones. There are no joins. There are no ways to have one table pull information from another table. So it's not that they're unrelated, because as you know, like we group them together in key spaces based on, how we think they're related, but they don't refer to one another at all. A variety of data types, like I just said, you could have a collection, you could have a document, is what I think MongoDB calls them. You could have a graph, you could have a key value pair. There are all kinds of, it's a lot more flexible in the types of data types that you could, that you can bring back. You have JSON objects. There's basically no end to the types of things that you can keep and store in your NoSQL database. And then I won't go into this super hard, but there is relaxed ACID properties. And so databases have like high ACID constraints. And so that's like atomicity, consistency, isolation, and durability. And NoSQL sort of trades off, like it relaxes those ACID properties. Oh, okay. Having some examples of what the data looks like on the slides.
We can keep moving past I'll gather some feedback for the presentation. Yeah.
Okay.
Yep, you're good.
Cool. So yes, so NoSQL, the whole thing about it is that it kind of relaxes all the strict constraints of a schema'd relational database in the hopes that the trade-offs, like the high throughput, the availability, the trade-offs make it worth it. Key concepts. So like I said before, NoSQL is a distributed database. So you can run it on multiple machines. You could have these machines on different continents. You could have them all in the same country. You could have them you could have them on the same block, whatever you like. But but this is different from a relational database where you might have them, you might have all your data stored on the same server, or in a single server farm or something like that. It is masterless, which means that all nodes in the ring, and you can kind of see like the description, or the visual description of Cassandra is usually depicted this way, which is there is a ring, and each one of these dots, we'll go into nodes in a second, but each one of these dots is a node. And so these nodes are all the same, and they're all capable of performing the same functionality. So reads, writes, they are all coordinators, they're all gossips, which we'll go into in a second. But when data is inserted into a Cassandra database, it's first hashed, and there's a function that's applied to the partition key on each record's. Each record has a partition key, and that's another kind of key concept in NoSQL. So it has a partition key. That partition key kind of tells, after it's done hashing, kind of tells Cassandra where in the ring it should be sent, like where will this information ultimately reside. And the output determines which node will get sent the data based on the token range. So I was saying before that a key concept for relational databases that data resides in only one place, and that's normalized. In Cassandra, and lots of NoSQL databases, but in Cassandra, there is something called a replication factor. And so you can determine how many copies of every single piece of information, every distinct piece of information you would like to end up with. So in the example here that's shown on the screen, the replication factor is 3. So every time a single record is inserted into Cassandra, there will be 3 copies ultimately on different nodes, ideally in different data centers, kind of spread out. But that is what makes Cassandra so highly available and fault tolerant. So if one of these nodes goes down, there are still 2 copies of this elsewhere available for clients that are making requests to read or write. The other thing is there's a consistency level. So you can say how many nodes that you'd like to report back. You'd like to report success back before you can acknowledge that a read or write was successful. So in this example, again, you have 3 nodes that will have that same piece of information written to it. You can say, I'd like only one node to, whenever a client makes a request and says like, hey, pull back this piece of information for me, you can say, well, maybe 1 is enough. It certainly would be faster, but if you want sort of more, the trade-off is like, do you want to be more sure that your information is right? Or do you want to be just quicker on the draw? So 1 would be super quick, but maybe you're not super confident in that information. 2, in this case, quorum is, it's like 51%. So if your replication factor is 3, then a quorum would be 2. If your replication factor was 5, it would be 3. But here you can say, I want to be more sure that this information is correct. So wait until you hear back from at least 2 of these nodes that this is the information I'm looking for. Let's move on. So nodes. Nodes are are a single instance of Cassandra. They're basically the building block to a cluster. So yeah, please.
Oh, sorry.
No, go ahead.
So you had that image, and it had like client and then to the node. And so you said that like any node can be the coordinator, right? I think my audio might have some delay.
I'm sorry, I think you cut out a little. Can you say that one more time?
Sorry, I'll write my question. I'll write my question out.
Okay. I think it was about this image. Oh, that's a great question. So Emma has asked whether any node can be the coordinator node. And so it's a great question. The answer is yes. And so every node in this ring that you see here has all the same information. So each node can be a coordinator. The client doesn't need to do anything to keep track of which node is the coordinator. The client makes a request, and then whichever node is available, basically, acts as the coordinator, because every single node knows which node that partition lives on. So they can say, okay, so you've made a request. Here is the token range. I know that that token range is assigned to, let's say, node A. And so it then sends that request to node A. And then it also knows, and you can see here like 3 lines kind of going out from the coordinator node. It knows that node A and node C and node B all are replicas of one another. They all have that piece of the partition. So if we're talking about, oh yeah, okay, great. So yeah, so it sends requests to all the replicas at the same time and waits to hear back from those replicas. Okay. Okay, nodes. So nodes are a single instance of Cassandra. There are nodes, and then there are what are called V nodes or virtual nodes. And so these virtual nodes, you can have, I think, 256 of them per node, which is, I think, maybe a little confusing. I think that it's fair that if that looking at this description, it is up to 256 virtual nodes per node. And so really all that they do is they further break up the partition. So you can kind of see down here that the partition key, oh, actually, we'll come back to that in a second. But if your partition is like the alphabet, or if if your primary key is like some letter of the alphabet, and let's say one of our nodes has A through C, right? So all of the requests that come in that have that as A, B, or C as a primary key are going to go to that node. And its replicas. So if you suddenly get an insane amount of requests for A, you can spin up more virtual nodes or V nodes so that you can kind of balance out and further break down that partition. So it's like, so you would break A into 100 parts or something like that, or B into 50 parts or something to kind of help like balance out the load and extend your storage capacity. So data centers, which you can kind of see here that nodes are kind of held in racks, and racks are held in data centers, and data centers collectively make up the cluster. So your data centers can be geographically spread out, which is one of the big benefits of NoSQL. When you have a data center in San Francisco, and you have another one in Europe, and you have another one in Hong Kong or wherever, you can be sure that like if something happens, like if there's a natural disaster, if you're doing maintenance and you have to go down, in Europe, let's say, that your clients are still well served by the data centers elsewhere that are located elsewhere. You have replication across these data centers. So you may have a complete set of your data across all the nodes in one data center, and you may have another copy of all of that data in a different data center, which again kind of helps you maintain all of your data. There's no single point of failure. There are multiple points of failure, right? So your power would have to go out in San Francisco, and there'd have to be a mudslide in somewhere in Europe, and there'd have to be like network issues in Hong Kong, all at the same time for your data to not be available. So in Cassandra, there is probably nothing more important than the partition key. So the partition key is how Cassandra works. So it's every piece of information is partitioned, and you can see sort of in the image on the screen, you can see here, this is an example where there is a partition key. It's actually a composite partition key. It's made up of two things, the sensor and the date. So we can see on the first line, the sensor is 1, the date is January 1st of 2015. And we know that every record that comes in that has a 1 sensor and that date of January 1st is going to go to the same node, whichever node it's assigned to. But all of the January 1st number 1 sensors are going to live in the same place. And so you could have multiple partitions on a single node, but you're never going to have one partition on multiple nodes, right? They're all together. And if you get a partition that is particularly large, let's say, again, kind of like I was saying before, where A through C for some reason is getting all the requests and the rest of the alphabet aren't, then you would want to rebalance or I mean, you could do it via virtual nodes, but you'd probably want to rebalance that. So that the partitions are equally distributed. So this is a good example of what happens when you have a partition key. Another part of your primary key is your clustering key. So this is part of how Cassandra sorts your data. One of the reasons Cassandra is so fast with I/O, with reads and writes, are because all of your information is sorted in the table, unlike relational databases, right? So relational databases like in the table are sort of unordered. In Cassandra, they know that the partition key is key, right, to keeping everything sorted. They also know that if you have clustering keys, those are kind of like additional bits of information that you require to then be sorted, either in ascending or descending order. And so when everything is sorted optimally, your reads and your writes are a lot faster, and the indexes that keep Cassandra just like really quickly looking through like large data heaps, like they require that. They need things to be sorted in order to pull back information a lot faster. The other thing is, I think that's probably, let me stop there. Does anybody have a question about primary keys, the partition key, the clustering key? No? Okay.
Can you hear me, or is it cutting
Oh,
out?
I can hear you. No, yeah, go
Okay.
ahead.
So here it's I'm looking at the bottom image where it says primary key, sensor date, and timestamp. Is that just an
Yeah.
example of what a primary key could be, or is it always the sensor date and timestamp?
No, this is just an example. Your
Okay.
primary key could be anything. So I spent a lot of time creating new tables, and so the thing that I never really had to think about before, I guess, and I think about now all the time is what is your optimal primary key? So what is your optimal like partition key? So the I guess I should say this. One of the really interesting things, and sometimes kind of a challenge with working with Cassandra, is that you have to kind of have an idea of like what kind of information you're going to be getting. And that's because your tables are keyed to queries. So actually, I think it was Jeff who said earlier that he worked with relational databases. In a relational database, you create the table and then you can query it however you like. In Cassandra, you have to know how you want to pull that information back because it is tuned to a query.
Yeah.
Yeah, so it's which is why the primary key is so important.
Right.
So if you know, so just like an example, if you're working in a bookstore and you have an inventory database full of inventory, right? You have to know, okay, so a lot of my queries are going to be like just me looking for a particular type of book, and maybe I have the genre of that book, but I don't have an author for it. So if you know that that is one way that you're going to be querying that information, then you would create a table that has, as a partition key, has genre, right?
Mhm.
Because partition keys are required.
Mhm.
You can't, unless you're doing like a select all, bring me back everything in the database or in the table. Um, then you are going to need a partition key. There's no other way to bring back information. So you can say partition key is genre, but maybe you are also looking for, that sometimes you're not just looking for any book, you're looking for like the book, like you're looking for, you have a title and you don't have the author or something like that. Then you would create yet another table. Cassandra loves tables, by the way. You're going to have tables for every use. So maybe you create another table that has as your primary key, or as your partition key, a title. And then yet another one that has author or something as a partition key. So basically for every use case, you'd create a table for it. The real art to it is creating a table where you can use for a bunch of different use cases. It's a little harder to do because then you have to really select your partition keys just like very carefully. But yeah, so this is so they can be anything. So you can have a primary key that is, a partition key that is a single value. You could have it that is, you can have it as a composite of like 2 or more values. But the clustering key is optional. You don't have to have it if you are querying a table and you have the partition key, but you don't have the clustering key, it'll still bring you back results. Yeah.
Thank you. That was really good.
Yay. Great question. Okay. So partitioning. And I think Lawrence, you asked about this earlier. So partitioning is important in Cassandra because it helps Cassandra control the size and balance the load, right? And so the size of the amount of data that is allocated to each partition is really important. It's important that it remains in balance because it affects read performance. I think I said earlier that indexing is a really important part of Cassandra. So if you're indexing a really large partition, it's going to slow everything down. And Cassandra is all about optimizing like milliseconds. Like it wants to give you back like just a little bit of time on each of your queries. And that maybe doesn't matter. It really doesn't matter if you're doing 10 or 100 or 1,000 queries a day. It matters if you're at scale, if you're doing millions and billions of queries a day. I don't think I mentioned this, but Cassandra was originally created, I think, by Facebook and released to the public in 2008. The same year, I think that Facebook released React to the public. Anyway, so this is really like an enterprise-tuned database solution because it really does shave off just like milliseconds on each of your queries by doing little things like this. So large partitions lead to large JVM heap sizes and inefficient garbage collection. And so again, so the more information that you're kind of storing as you're indexing these partitions, like the more waste there is. And then also one of the features of Cassandra is that it allows you to make repairs to bad data. And it also allows you to tombstone, which is kind of a fun way. Tombstone eviction, I think it's actually called, but it allows you to put an expiration date on your data. So if you are, yeah, exactly. Good job. Thank you, Lawrence. Yeah, so if you are working with data and you know that like you're querying or you're storing information that is not going to be good in a year, like let's say it's just like an annual report of something that you're going to replace, that you're going to run every year and you're going to replace it every year. So the information from last year is no good to you, right? And you don't want to store it. As you're entering this information in, or as you're creating a table, you can select what they call a time to live, which is the expiration date. So you can say like, this information is no good to me after a year and a month. And then it will, it'll mark it for eviction or deletion and then remove it from your table. So that's another way that it's like, instead of storing, like there's no means to do this in a relational database or to automate this really. So if you're storing like a crazy amount of data, unless somebody is going in and deleting this data, it's just going to live there for take up and cost you a lot of money. To um, um, next, we're going to talk about distributed, like how Cassandra is distributed. So I think I said this before, but distinct and geographically diverse data centers are kind of what Cassandra was built for. And so it allows for disaster recovery, allows for maintenance, it allows for you to, if you have like a really, if you are Facebook or something like that, and you have clients in every country of the world, and you're getting a lot of queries from every country in the world, you're going to want, again, this is like milliseconds on each of your query, but you're going to want this information closer to the people who are going to be querying it. So it lightens the load if you have a data center. It's all in the same cluster, but if you have a data center in Europe, then all of your requests in Europe may go there. If you have a data center in Asia, then all of your like East Asian requests might go there, and same for the US. And that's actually a big reason that a lot of people use Cassandra. So it's the same information, but is accessible by clients in kind of all different parts of the world without slowing. There's no latency to it. There's no cost to it. Oh yeah, low latency. There it is. And the other thing is, if you have copies of your database, then you can use it for different purposes, right? So you might have data that is just available for a client request, but you also might want to run analytics on that data. And so it slows it down to be doing the same thing on a single copy of your data, but you might want to have a copy for public consumption and a copy for you to run your analytics on. Tables. So, oh no. Okay, so tables in Cassandra are a little bit different than relational database tables. They were formerly called column families, which I think everybody found so confusing that they did eventually change it in the documentation, change the term to tables. But you can add, unlike sort of like a rigid table in relational database where, again, you have like a cell at the intersection of each column and row. In Cassandra, you have columns, and then you can there can be a cell at that intersection, or they cannot be a cell at that intersection. It does not force every column on every row. So you could have so actually, as you can see here, right? So the second row doesn't have 3 columns, and that's totally fine. That's allowable. The only thing that it absolutely must have is the partition key. Yeah. So relational database schemas are fixed, and once defined, every row must have a value for every column. Cassandra does not force all columns on every row. It can have any number of columns in any row. It's also sometimes called a wide column model. It's based on Big Table, which I think is Google's Big Table. But Big Table is a wide column model, which means that you can have literally like any number of columns on any rows, and you can have none other than the partition key on the next row. There is, I don't think we have time for it, but the tables are information that you write to Cassandra is stored on SS tables and meme tables, or mem tables, they're sometimes called, and they are stored at table level. So every write is saved first to an immutable commit log, and then is saved to a mem table. This mem table lives in memory, and so instead of having to access the disk every single time somebody makes a query, really what is probably happening is it's your request, the node is accessing the mem table for it. And so it's a lot it's using fewer resources, it's faster. And so it reads from the mem table, and then mem tables are eventually flushed to the SS table, which is on disk. Okay, is it kind of like, so Emma, your question is it kind of like caching? You're talking about the mem tables?
Yeah.
Yeah. Um, It well, it it's sort of like hashing. What it really is that every for every record, right? You kind of have the mem table has like in its memory what it last looked like, and then every time somebody makes a write to it, it is writing like underneath it, like like this is the most updated information for this cell. This is the most updated information for this cell, and so when somebody queries it, when there's a read request for that particular cell, it finds the latest information and just pulls that back.
Oh.
So yeah, it's
Okay.
really yeah, it's interesting because I mean, I guess it's sort of like caching in the sense it's not actually reading from disk every time, but it is finding you the most updated information that that node knows about. Um, yeah.
Okay, thanks.
Yeah. There's something I think a fun name. It's called Gossip Protocol. Gossip Protocol is another way that Cassandra is um, makes itself very available. And so one of the things, Gossip Protocol is peer-to-peer communication. And when they say peer-to-peer, I mean like node to node. So these nodes keep in pretty consistent contact about what information it has received, what information it knows about what of what information other nodes have received, because really what they'd like is for each node to have an idea of what are the most recent writes, and what what partition is kept on which node. Um, this is how Cassandra keeps itself consistent. And so it enforces the replication factor. And by that, I mean, gossip is how we know how many, like if you have a write to one node and that node has two other replicas, this is how they communicate with one another to say, okay, we've contacted that one node. We now have to contact the two other nodes. This is like the coordinator node has to contact two other nodes to let it know that there is a write or there's a read request or something like that. So it's basically just like a networked communication protocol. And so nodes periodically exchange state information, steady state event information about themselves and other nodes that they've gossiped with. They keep an updated list of node membership at each node. So this is, again, helpful to know. It's sort of like a topology. Like it needs to know what else is going on, where everything is in the node. And that way, again, when it gets a request, it can send it to the most appropriate node for that request. Let's see. And then you see this term eventually consistent. And I am going to wait until we get to, yes, to this slide. So CAP theorem is a theory that is, or a theorem that is applied and is born of like NoSQL, right? So it says that on this list of consistency, availability, and partitioning. And this is not partitioning as Lawrence described it earlier. This is partitioning in the sense of, is there a network failure? Are these nodes not able to communicate with each other? So that's the other definition of partitioning when it comes to databases. But so in this list of these three things, C, A, and P, you can only ever have at most two of them, right? Your database management system can be consistent and available. It can be available and partition tolerant, or it can be consistent and partition tolerant. And so does anybody want to just take a super quick guess as to what you think? Yeah, yeah. They aren't exactly the same thing. That's a really good point. I think there are way too many acronyms, Lawrence, I agree. But can anyone guess what they think Cassandra is? If we know that you can only really prioritized two, and then the third one is kind of dropped off. Like from what we've talked about here, do we think that Cassandra is consistent and available and partition tolerant? And when I say partition tolerant, I mean, does the system continue to work expected even in the presence of partial network failure? Oh, yay! These are, so I see Lawrence has said A and P, available and partition tolerant. Emma has also said A and P. That is correct. Yeah. And so it is available and partition tolerant, which means that it most prizes availability, which is, does anybody who places a request, does any client, does every client get a response? And the answer is yes. And then it also prioritizes partition tolerance, which means that in the event that these nodes can't communicate with one another, are they still able to provide information? And again, the answer is yes, based on their structure, because they're masterless, because each node is able to read and write and perform gossip and all on their own. So the other thing I will say is that the consistency element, if you're curious, relational databases are often described as available and consistent. And so, but the consistency element, Cassandra kind of makes the trade-off that that all nodes will become eventually consistent, and which means that if for some reason a node goes down, and while it's down, there are reads and writes happening, and so it doesn't know, because it doesn't know the newest writes, because there was some sort of system failure and that node or that entire rack went down, it will catch up and it will become, and then eventually it will become consistent again. But Cassandra is like okay with that trade-off. And it makes that trade-off because being like available, being super fast, even if it's not super consistent, is what it seems like a lot of enterprise solutions are looking for. So just to wrap up before I take more questions and kind of open it up more, if you were asking yourself, is Cassandra the one for you for whatever your project is? The pros are that it's super, super fast because of that trade-off. It is low cost because you're not dealing with like physical computing upgrades. You're not, adding more memory or something like that to your server or your database. It's open source, which I think of as a huge pro, and I think a lot of people do too. It also adds to the low cost element of it. It's highly available, because there's no single point of failure, which means that it's up and working, and people kind of, just because like there's a system outage or something like that, a network outage or something, your system doesn't go down completely. It is eventually consistent. So these nodes that maybe have gone down will come back up, and they will eventually become current with the information that they have. It's highly tunable. I don't think we talked about it much here, but a lot of Cassandra is configurable. So you can there are a lot of decisions that you can make that you can't really make in a relational database. And then there are the elements of recovery and repair. So you can repair bad data. Cassandra has a grace period where when it finds bad data, it will give you, I think it's configurable, but I think it's like by default 10 days or something like that to fix it. You can run repair over an entire partition. You can run what they call incremental repair, which is where you just say, I just want to look at the kind of the changes from the last time I've run an incremental repair, and make changes to bad data then. So there are a lot of, this is partially why people call it self-healing. And then there are some real cons to it too. So it does require, when we were talking about queries, we talked about how much knowledge you have to have about how people will be using this or what kind of information you want to call up, what you want your view to look like. So it does require some knowledge of how data will be used, and kind of more consideration, more forethought than you might need with a relational database, just in terms of like what kind of information, um, what kind of views you'll want to return. It's also um, because there's a lot of tables that cover the same information. You will see some redundancy, some it's all denormalized. There are implications for storage. Those storage implications also have like a huge trade-off though, because while you may see the same information located in a bunch of different places, you also have things like the recovery repair and the tombstone eviction that gets rid of old bad data, the indexing, which like loads that JVM hip does, and kind of again, like it's lag time. There's a little bit of time where your writes may be lagging, and so one node may not have all the information that other nodes may. So that is. I did include more information. There's the Apache Cassandra documentation. There's a really good article about Cassandra architecture. There's more information about the cap theory and normalization. There is a really good intro YouTube video. I think it's 30 minutes to an hour. I think it's maybe a little less than that. But it explains the different normal forms all the way, I think up to 5, which nobody ever uses. And then there are a bunch of use cases in Planet Cassandra. So I will stop there and just ask if we can, if anybody has questions, if there are things that I maybe didn't cover, if you have questions about.
I always have questions.
Yeah.
So you mentioned that you're using Kafka and Cassandra. And as you were talking about Cassandra, I noticed that there are a lot of overlaps in like what Cassandra does and like the pros of Cassandra and Kafka. When I was using Kafka, we were querying on Kafka using KSQL, which was not the best. And it was pretty slow. And it seems like Cassandra is like very queryable and like fast to query. So anyway, I'm just wondering if you could talk about like where you got like why you're using both, how they overlap, like yeah. Or if you can talk about that.
I can, yeah.
Okay. I wasn't sure if you were like allowed.
Yeah,
I didn't want to not a spy, I promise.
So it's a really great question. The thing that I really enjoy about using both Apache products at the same time is that they really do dovetail, and a lot of the key concepts, like their structure, like you were saying before, like the kind of like the ring architecture, and I mean, they're just very similar. And so if you're working with one, it seems very natural to move to the other. And I know that Kafka is also very partition focused and kind of has the same idea that like almost everything is the partition because everything is how we store this data. Everything is how we sort and store this data. And so it's nice to be able to work with both those products at the same time. I'm trying to think of if there is an example that I can give, but I mean, I guess technically you could use anything with Cassandra and vice versa, but it does seem like it's just like a lot of their architecture, a lot of the key concepts to them are just very similar.
Yeah.
Yeah.
And do you use Cassandra as like a persistence layer where and like you're using Kafka in kind of like a almost like a intermediate like persistence kind of way, like
Yeah, so the way that we use it, I think I can say this. The way that we use it in our app is basically that Cassandra is like it's like message orchestration. It's like how we get messages like within the app, and then when we want to persist the data, when we've kind of manipulated it all we can, and we want to store it. We will then write it to Cassandra,
Okay.
and then we also use Databricks, and so that's like another another layer on top of that. But it's great because I think Kafka is the same way. We do batch processing, and so if you're batching like 10,000 records at a time, or 10,000 like Kafka messages at a time, it's actually super nice to know that it's like very all or nothing. Like this batch is going to be processed or it's not. At least with Spring Batch, that's how it works. But yeah, so just like very similar concepts. Yeah.
Gotcha. And then you query straight to Cassandra then.
Mhm.
You don't query to Kafka. Okay.
No, I've never queried Kafka. That's so interesting. Oh, you know what? I will say as a fun fact, oh yeah. Um, As a fun fact, though, the before I started working on this project and started working with Kafka and Cassandra, I went to Emma Richardson's talk in 2022, December 2022, and she talked like wonderfully and really interestingly and richly about Kafka, and I was just like, I have to work with this thing, and then a month later, I joined this project, and have been working with it ever since, and so I guess the secret is real. Um, yeah. Oh yeah, there are oh hey. Yes. I want to say super quickly, Lawrence mentioned sort of the difference between SQL and CQL, which is the language that Cassandra is written in, or queried in. And so even though syntax and terminology are largely the same, like you can really see what's missing from CQL that is maybe present in SQL, like joins and group by and order by and stuff like that. But the really cool thing about it, the thing that I like really flipped when I learned was that you can return objects, um, you can return collections, you can iterate through collections with CQL, which is really cool. It's also like a little bit briefer than SQL because all clauses are optional. So like your wheres and your froms and your selects are sort of optional. So anyway, so that's really cool. SQL is really cool. SQL is really cool in that it supports like very complex transactions, where CQL doesn't really as much, but it doesn't need to because again, these tables are so finely tuned to queries that you don't have to do as much transacting in the query. Yeah, SQL does look exactly like if you're just reading them, you really can't tell them apart. I mean, I think CQL looks a little bit more like more natural, like a little bit more like human speak, just a tiny bit, but they're very similar and they're meant to be. Um, I think it's meant to lure people over to Cassandra. Um, let's see if there's anything. I think that's kind of everything that I had prepared, I suppose. Anybody have any last questions? Lauren seems pretty up to date on stuff. I would be very curious to know like what your background with NoSQL is or with Cassandra. It seems like you've got a lot of knowledge, my friend.
And feel free to take yourself off mute to chat. Just
Well,
curious.
curiosity, yeah, there's the nice thing about NoSQL is that it's kind of buzzy right now, and so there are a lot of resources, and there are a lot of so to yours asked, yes, exactly. There are a lot of resources out there, which is great, and there and a lot of NoSQL database management systems are open source, which is great. It makes it a lot more accessible, I think, to people who aren't big businesses. And there are also lots of different types of them. I was reading a use case for Amazon Neptune, and they talked about how they used NoSQL in cloud computing security, and how using graphs as opposed to sort of like typical tables or even key value pairs was like the key to solving a lot of, or like identifying a lot of like security risks before they became critical. And it's really interesting the kind of, if you kind of unlearn what you think of as a table or as a database, it's wild to see how many options are out there for the application of NoSQL.
When you were talking about like oh, sorry, there's a hand up.
Oh,
or Latha, I'm sorry.
They think you're mute.
Yeah, hi. Hi. Can you hear me?
yes.
Okay, thank you. I just had firstly, yeah, I would like to thank Vinyate, is it? I
Oh,
hope I'm
Wintaye. Yes. Yeah.
Wintaye. Yeah, thank you for the presentation. Yeah, it was very well detailed, and thanks for including the links. I would like to refer to them. So I had two things. One, would it be possible to share the link to the slides so that I can refer to them? And second thing is, if I'm interested in getting in touch with you, would you be open to any mentoring related to databases and that sort of topic? Because I am trying to make a switch career wise, and I'm looking for some mentorship. Yeah, these were my two questions. Thank you.
Yeah, absolutely. I love talking about NoSQL. I'd love to talk about, I mean, I had a very I guess late career switch in a non-conventional path. So I'd love to, I'd love to connect, love to talk to you.
Thank you. Appreciate it.
Yeah.
Because I've just felt lately that when I'm learning a couple of skills at a time, not just one of them, and some things are overwhelming for me, not because I don't understand. For example, CAP theorem, I've not worked on it. I've not worked on like system level design as such. I've been a tester, but lately recently when I learned CAP theorem, I could guess the answer, right, for your question. Why is it A and P? Like Discord also uses A and P, if I'm not wrong. So like I like the practical things, and I feel mentorship would help me in that direction. That's why.
Sure. Yeah, I'm happy to share any information I've gleaned on NoSQL or Cassandra or things like this. Like, yeah, happy to share. Yeah.
Like, how may I connect with you? Like, is there an email address, or would it be through LinkedIn?
Yep. This is you're
You
welcome
shall
to
receive.
screenshot that. Feel free. Yeah. Feel free to email me, LinkedIn, message me, stop me on the street, whatever, whatever you'd like.
Maybe don't
Yeah,
do that.
definitely not.